afternoon, everybody. We're going to start the last session of the workshop. So we'll start with Alan Hernandez that is going to talk about offshore couplings. So go ahead, please.
Hi, thank you so much for coming the last day and after the lunch. Maybe it is very difficult to go. Well, I'm Alan, and the name of my work is Offshell Couplings. And thank you for the opportunity to be here. And this work is in collaboration with Dr. Arturo Fernandez Telles and Roberto Tavares and Agustin Moyoki. So, well, I would like to introduce some terms that we will use in this talk. So first, what we understand for an offshell coupling, well, and for this kind of couplings, we require at least one external virtual particle. This virtual particle normally are denoted by an asterisk. For example, here I show an offshell C boson and offshell Higgs boson and offshell W Gauge boson, right? So all these particles are virtual, and well, in this talk we only consider couplings with offshell bosons, right? Well, the last thing I want to say is that the following Q is the form momentum of the offshell boson. Okay. So I want to give the motivation of this work. The offshell couplings are of a very great interest in recent years. For example, the gluon top anti-top, the gluon top and anti-top coupling, especially the top quarter anomalous coupling. And in this case, the chromomagnetic dipole moment has been very studied in the last years, because there are a lot of disagreement with calculation. First, I want to know that when the gluon is on shell, we have this condition, Q squared is equal to 0. Remember, Q in this case, the form momentum of the gluon. Well, when the gluon is on shell, we have this condition. And for this condition, we are working at a very low energy level of the coupling constant. As you know, the QCD coupling constant is very strong at very low energies. So at this energy level, the chromomagnetic dipole moment is not well defined. So it can be studied in the perturbative theory. Additionally to this problem, for a non-shell gluon, it's been found that a non-finite chromomagnetic dipole moment is found. So it is very problematic because it is supposed to be observable, and this observable must be finite, right? So on the other hand, the last year, two different collaborations here in Mexico have studied this coupling, but for the case of an offshell gluon, and in this case, it's been found that the chromomagnetic dipole moment is finite, and in this case, we can work in a perturbative limit because we can study this observable in, for example, energies of the C boson mass, and at that level, the QCD coupling constant is very low, and well, we can study through the perturbative theory. So another example is are the trilinear neutral gauge bosons coupling, which cannot exist at true level in the standard model, but they can be induced at one level. So here I show all the examples about these couplings. For example, on the left side, there are two on-shell C bosons and an UV off-shell boson. In this case, this UV can be an off-shell C boson or an off-shell photon. The another possibility is where we have a real C boson and a real photon, and again we have this UV off-shell boson, which again it can be the C boson or the photon. Well, here I show the vertex function of this coupling, which is this expression. This is the vertex function, and it is proportional to this factor. Again, remember that Q, the form momentum of the off-shell boson, and in this case, when the B boson goes on shell, we have the following condition, and you can note that the vertex function is on zero. So the linear difference boson while this one off-shell boson looks like, right? Well, this year, very recently, the EMS collaboration reported the field for the first time the evidence of an off-shell Higgs boson. This off-shell Higgs boson is supposed to decay into two real C bosons, and which decay into leptons. So we have 4 leptons in the final state. And from this process, the best result for the total width of the Higgs boson has been obtained by the CMS collaboration. And well, this is the best result for the total width of the Higgs boson. And additionally, the result agrees with the standard model. And well, as you know, the mass of the mass of the Higgs boson is less than 2 times the mass of the Higgs boson. Thus, to obtain this process, the Higgs boson must be off-shell, because an on-shell Higgs boson cannot decay into 2 on-shell C bosons, right? Well, another motivation to study this kind of coupling is that we can introduce the anomalous coupling through effective Lagrangians. And in this case, first I show the vertex functions for the gluon top anti-top coupling, which can be written as I show here. This term corresponds to the chromomagnetic dipole moment, and this to the chromoelectric dipole moment. For the linear neutral gauge boson couplings, the vertex function can be parameterized in terms of 2 form factors, F4 and F5. Here I show the case for 2 real C bosons, but for the other case that I told before, we have a very similar parameterization. For the case of the anomalous coupling, for the coupling of 2 C bosons and the Higgs boson, well, we can also introduce these anomalous couplings in this form. Here, these H form factors are in terms of the anomalous couplings, but I don't discuss that part in detail here. But I want to mention that for this kind of coupling, we can 2 possible off-shell coupling. First, we can have an Higgs boson off-shell, and the 2 C boson must be on-shell, right? And the other case is, we have a C boson off-shell, and thus we have the Higgs boson is on-shell, and another C boson is also on-shell. Well, as we are discussing about off-shell coupling, these anomalous couplings must be function of Q squared. Remember, Q is the form momentum of the off-shell boson, and well, this is very interesting because, for example, in QED for the for the magnetic dipole moment, it is a constant. It is not function of any momentum, right? So these kind of couplings are also very interesting because these 3 terms, I want to note Here I show the chromoelectric dipole moment, the form factor F4 and the form factor H3. Well, these form factors are related to CP violation. Remember, CP violation is necessary to explain the invariance between matter and antimatter in the universe. And we can say that through, we can say that with this kind of coupling, we can also obtain a new source of CP violation, which are very necessary, as I explained. So, well, you can say this is only the theory. Are this kind of coupling really, really important? Well, I say they are important because they are being searched in at the LHC. Here I show the most recent limits for all the anomalous couplings. Here I show the results for the chromomagnetic dipole moment and the chromoelectric dipole moment of the top quark. And here I show some constraints on the linear network gauge boson coupling. I don't show all the results, but for all the possibilities of this kind of couplings, there are available results. For the case of two C boson and a Higgs boson coupling, there are also indirect bonds. And what I want you not hear is that these kind of couplings are considered as real observables at the LHC. This looks very normal. This looks okay. Maybe it's not interesting, but I want you to keep that in mind. So they are considered as real observables at the at the LHC. Okay, so we know we have to calculate off-shell observables, but the calculation cannot be very clear. So for the case when we have on-shell particles, on-shell external particles, the on-shell green functions, we know that they are gauge invariant and gauge independent. Well, these are really good news because we don't need to worry about the gauge invariance. But for the off-shell green functions, they are not necessarily gauge invariant and gauge independent. So this is a problem because the calculation of this kind of anomalous coupling is not trivial. What I want to say here. So now for this kind of calculation, we must find a way to obtain well-behaved observable from off-shell couplings where this new approach to extract all observables. And there are a technique, the so-called pinch technique, which is a diagrammatic method that combines self-energies, vertex, and box diagrams related to the related to the physical process. For example, they are related to in the case of the gluon top anti-top coupling, we have some cell energies of the gluon and the top quark. Well, this method or this technique seems to be very difficult, but we also have the background field method, which is very useful in the quantum field theory, and especially when we fix the gauge to the Feynman-Topf gauge. In this case, it's been proved that the background field method and the pinch technique are equivalent. So we have two approaches to extract or well-behaved observables. In general, we use the background field method because, as I said, the pinch technique requires a lot of Feynman diagrams, which could be very difficult to calculate. And so here I want to show some Feynman diagrams, which are necessary to induce the chromoelectric dipole moment at the one loop level in the standard model. The anomalous couplings are induced at one loop level, or maybe more. For example, the chromoelectric dipole moment is only induced at least at 3 level in the standard model. But as I said, the chromomagnetic dipole moment is induced at one loop level in the standard model. Here I show the QCD contributions and the electroweak contributions to the chromomagnetic dipole moment of the top quark. And well, I also show the case for the linear neutral gauge boson couplings. In the standard model, they only can exist at one loop level. And well, here I show the contributing Feynman diagram for these couplings in a flavor changing, sorry, in a beyond standard model where flavor changing neutral currents are permitted. But for the case of the standard model, we have the same masses for all the fermions in the loop, right? Well, for the coupling of two C bosons and a Higgs boson, we also have one loop contributions for in the standard model. Here I show only some diagrams, some contributing Feynman diagrams to the anomalous couplings. There are more diagrams. I don't remember the number now. I think there are more than 40 diagrams. But what I would like you not hear is that all the particles in the loops are virtual, right? For all the cases, all the particles in the loops are virtuals. That's what I would like you not hear. So at this point, I'm going to call to the optical theorem for Feynman diagrams, right? This is a part of the famous book of Peskin and Schroeder, and I want you know the following part, which says a Feynman diagram, two yields, and an imaginary part for the amplitude only when the virtual particles in the diagram go on shell. So this means that in this Feynman diagram, remember that Q in this case is the form momentum of the Higgs boson. For Q equal or higher than 2 times the mass of the fermion connected to, or the fermion in the loop, then the amplitude of this Feynman diagram will acquire an imaginary part, and in general, the amplitude will be complex, right? So we know that we have an amplitude complex, and we can extract well-behaved functions or well-behaved observables from this amplitude. And well, but what we said before, well, remember I said you have to keep in mind that at the LHC, this kind of couplings are considered only as real observables. But for our discussion, well, we can say that our anomalous couplings for the off-shell couplings may be complex, right? So we have an imaginary part for these observables, which are not considered or studied at the LHC. And when before to proceed to more about the LHC, I want to discuss some numerical results for the chromomagnetic dipole moment standard model. On the left side, I show the real contribution from this Feynman diagram to the top quark chromomagnetic dipole moment. But in the right side, I want you to note we obtain the imaginary part. So this is the optical theorem, right? So I want you to note here, as the optical theorem says, the contributions, the imaginary contributions are different from zero for energies where the fermions connected to the gluon can be on shell. So this is the optical theorem, as I say. And again, this kind of couplings of anomalous couplings are in general complex, and at the LHC they are treated only as real. So where are the imaginary parts? Well, for the linear network gauge boson couplings, we have the same result. They are in general complex. I show only one example, the case for two real C boson and off-shell C boson. I show this plot, which is not the original from this famous article, a reproduction. But I want to note that the dashed line is the contribution. Sorry, this is the imaginary part of factor 5. Imaginary contribution corresponds part in the standard model, we have the same particle in the loop. So the relevant result or the relevant imaginary contribution correspond to the top quark. So please note that this imaginary contribution is not zero for energies where the top quarks connected to the off-shell C boson in this case can be on shell. So again, this is the optical theorem, and this kind of couplings are considered only as real, observable at the LHC. So where are the imaginary parts? And now I want to discuss the case, or I want to show numerical results for the case when we have an off-shell C boson and two real C boson in the standard model. I don't discuss all the results in detail here, but I want to show that, again, we have the same behavior. This kind of coupling, this kind of anomalous couplings are also complex in general, right? And again, if we compare with the standard model, sorry, with the LHC results, they are only constrained as real observables. And well, also, we can observe from these plots that in general, the imaginary parts, so the imaginary parts are of the same order of the real part. So maybe, or at some energies level, the imaginary parts are higher than the real part. So I think, or I say that the imaginary part could be relevant and it should be studied at the LHC. So to achieve or to see the contribution of the imaginary part at the LHC, I want to study the contribution in the top pair, in the top anti-top production at the LHC, where we have, or I show here the contributing Feynman diagrams to this process at the LHC, and we have to calculate two different cross sections. We are including the anomalous couplings, the gluon top anti-top coupling, which are the magnetic and chromoelectric dipole moment. So in this case, these two cross sections can be written in this form. This is a very famous result, and well, here they consider it as real, the anomalous coupling. But as I said, I want to study the implications of the imaginary parts. So if I write the anomalous couplings as explicitly as a complex number, with the real and the imaginary part, I obtain the following result. So we can observe in general that more terms appear when the anomalous couplings are considered as complex explicitly. So what I say is that the effects of the imaginary parts may have been neglected in classical calculations. So again, I say these imaginary parts could be very relevant at daily. So we study some kinematical distributions for the top pair production at the LHC, and I didn't found any relevant result. Actually, we consider different case for the imaginary parts, but they look very similar to the case where we only consider anomalous couplings as reals, right? So it looks a little sad, but this is not the end of the story. Now, we also want to calculate this kind of off-shell decays. As I say before, this process was reported by the CMS collaboration this year, and well, what I want not here is that, again, these kind of calculations are not trivial. For example, we need to use the complex mass scheme. We must to change the Wigner distribution for this kind of distribution, where this mu h is an input parameter, which is also similar to the on-shell mass, and this gamma h is similar. It's also a parameter, but it can be also similar to the total weight of the Higgs boson, right? So there are another kind of decays where for example, an off-shell Higgs boson, sorry, C boson can be produced from a quark antiquark, and this off-shell Higgs boson can decay into a real C boson and an on-shell Higgs boson. So for this process, again, it is not trivial, the calculation. So we need to consider an extra polarization for the off-shell C boson. Well, but now I want to talk about my current work. So this is work in progress. So we're interested in this process. And at some point in this process, you need to calculate the partial width of the off-shell boson decaying into two real C bosons. So again, I want to study the contribution of the imaginary parts, and we consider the anomalous couplings. As I explained at the beginning, we can parameterize the anomalous coupling in this form for the coupling to the bottom slide. So I write the anomalous couplings in terms of the real and imaginary part, because I think they are complex for the case of off-shell Higgs boson. And again, we do not find any relevant result, but once again, not the end of the story. So now we want to study the process. We want to study the polarizations of the C boson. So the total width, or we can calculate this partial width, where the Higgs boson decay in two C polarized C bosons. We have these three combinations. The other kind of combination are 0 and well. So again, we consider the anomalous couplings as complex, and we find that that each partial width increase from 4% to 30%. So, but this only happens when we include the imaginary parts. So, what I say here is that the imaginary part seem to be relevant when we study the polarization of the C boson. But I have one more result I want to tell you. Again, this is the vertex function of the coupling of two C bosons and a Higgs boson. And again, I want to study the contribution of this complex, of the imaginary part. But this time I want to, or I define the following asymmetry. We take the difference between the production of the difference between the production of the transverse polarization. Here I go again. We take the difference between the production of the difference between the production of the polarized C boson, and well, we find if we again use this expression here, where we use the real and the imaginary parts of the anomalous couplings, well, the asymmetry is proportional to these terms. So I want to note that in the standard model, this kind of asymmetry is 0, but if we include anomalous coupling, it is not 0. So it is very interesting. But so I want to note that, remember, I said at the beginning, H3 is related to CP violation. So we require CP violation to obtain this anomaly. But you also require the complex form of the anomalous coupling to induce this asymmetry. So, in brief, to obtain an asymmetry different of zero, it is necessary CP violation and the complex anomalous coupling. Again, in classical calculation, these kind of couplings are not considered as complex. What I'm saying is that the imaginary parts are relevant and well, we don't know if we can measure the polarization of the two C bosons, but I think that the polarization of the C bosons maybe they have implications in the final step, in the final state where we have four leptons. So my summary, well, complex anomalous couplings can be obtained from off-shell couplings. The imaginary parts may be relevant in some process, and maybe they are not well understood. The polarization of the gauge boson may be sensitive to the imaginary part and also to the CP violation. And there are many processes where the imaginary parts have not been studied. For instance, a process where we have the trinomial neutral gauge boson coupling, as I showed here. That's all. Thanks so much for your time.
Thanks a lot, Alan. We have time for questions. Is there any question? Thank you. It was very interesting. I am curious when you show so many diagrams. I guess that, for instance, to achieve gauge invariance and also finiteness of the result, maybe you don't need them all.
Sorry, the what?
In order to achieve gauge invariance and cancellation of UV divergences, I guess you don't need all the diagrams, all right?
No, we only need, for example, here, this diagram where we have only fermions in the loop, it is gauge invariant always.
Yeah.
So we don't require all the Fermat diagrams. For example, where we have gauge bosons, or the Golson, thank you. We require, well, they are a little tricky.
Then, since you know all that, perhaps you can also see the numerical effects of given diagram, and maybe you can get to some simplified expression that can be more useful to get to the sensitivity in a closed form or something like that. Have you thought about that?
No, we haven't studied that part now, but it will be a very good idea for the future.
And I have other comment, but we can discuss privately since we will.
Thank you.
Thank you for the presentation. You say that in progress, you are going to calculate the factor selection. Is there any difference? I mean, we are going to recapitulate using four leptons, the final state, but we are going to combine electron and muon, or we are going to reconstruct first using, for example, 4 electrons and later 4 muons, the combination.
We don't really know yet because we are only in this part, but as you said, we have to study that part, but this is work in progress. But thank you for your question.
Okay, thank you.
Time for last question.
When you mention about these anomalous couplings that are complex, if you use the representation as a real, the magnitude and a phase for the complex number, then you have another interpretation for the phase, for the complex part as a phase. And
Okay,
I-
that's
I-
correct. Yeah.
And I was wondering, in that case, this last term that you are mentioning that is CP violating, because of the Levi-Civita part, once you have an imaginary term, which also has CP violating term, that probably you have a contribution which is not CP violating term. That will be interesting because it's not, it's coming from this imaginary contribution in that term that makes CP non-violating contribution. That would be interesting to see. And the other point is, I was wondering about the, well, that was a comment. In the decay to CV to for leptons, one of the possibilities that people has used to measure the decay width of the Higgs is exactly going to that channel and see in the on shell of the both the two C bosons. So have you tried to check in that region how these results behave? That would be interesting because people is looking at exactly at that kinematical region.
Yeah,
Next.
we are trying, but at this point we are only in the calculation in the calculation of this park. So we have no more results, but as you said, that's a possibility, and I think this is very interesting. So thank you so much for your comment.
Thank the speaker again. We move to the next one. Our next speaker is Rogelio Reyes Almanza from Sinvestav. He's going to talk about the search for heavy resonance high intensity or CW and action like particles, no resonance or pH production at certain pH. Please go ahead.
Sorry for the long title. I could have made it shorter, but it's essential the title of the paper that was published this March. So I will show you a work that I did as postdoc at Universidad Autónoma de Madrid. And the motivation of this analysis is despite the standard model has been experimentally tested and has been successful, there are open questions that we try to solve by proposing new bosons like extensions of the standard model. Most of these theoretical proposals can be simplified in models which make general predictions on specific observable processes. In particular, the heavy resonances are useful because we can use to test new physics scenarios with minimal assumptions. Two well-known examples of that are in the heavy vector triplet framework, where the proposing are, well, the proposal are W prime or C prime. And in this framework, we found two models. The first one is a weakly coupled scenario where the coupling is equal to 1 and the branching ratios to fermions and electroweak bosons are similar. And the next one is an strongly coupled scenario with typical of composite Higgs models. And the branching ratios to electroweak bosons are dominant, and the sensitivity is dominated by the boson analysis. Other one is the graviton in the warp extra dimension model, which depends only one parameter, and the case of this graviton to top Higgs or electroweak bosons are dominant. Another theoretical model that has become popular in the recent years are the action line particles. So these kind of particles are well motivated theoretically as neutral pseudo-Goldstone bosons of a new spontaneously broken symmetry. The interactions of the Alps can be parameterized with an general effective field theory Lagrangian consisted with the standard model gauge symmetries and CPs. And we found two implementation of this EFT Lagrangian. The linear version related to weakly coupled new physics with minimal parameters in the Lagrangian, and the second version, the chiral version, related to externally coupled new physics models with more parameters in the Lagrangian. The Alps interactions are derivative, which means they depend on the momentum. In particular, here they grow with the momentum, and the couplings are proportional to Wilson coefficients and inversely proportional to new physics energy scale FP, which is a real advantage for high energy experiments. Colliders allow searches in a wide range of Alp masses and couplings. At the LHC, for example, the natural sensitivity is to FA scales in the TV region. In particular, the gluon-initiated Alp-mediated processes provide new possibilities to test the Alp universe beyond the classical searchers to gluons or photons. These channels are sensitive to the product of the Alp couplings to gluons times the coupling to electroweak bosons. Here I show you two examples of these channels where the Alp is acting as a mediator, and the coupling is to CC, electroweak bosons in the linear version, and the chiral version on the right is coupling to C boson and 1 Higgs. So this off-shell production is very promising because the cross-section are large enough to constrain significantly the theoretical models using data. Alps in this kind of processes is an S-channel mediator in the gluon-gluon to diboson productions with the energy of the system much greater than the square of the mass of the Alp. The size of the S-hat is enhanced by the mass threshold of the on-shell diboson system, but most importantly by the RPT spectrum provided by the derivative couplings. So the analysis uses diboson searches looking for high PT or high mass deviations in the tails of the transfer momentum or mass spectra with respect to the standard model expectations. We found that for Alps light enough, the cross-sections, kinematical distributions, and expected limits are found to be independent of the mass of the Alp from the very light limit up to masses around of 100 GeV. Typically, the models of diboson resonances are on this mechanism, the gluon-gluon fusion, the Drell-Yan, and the vector boson fusion. And we focus on the first two, and we use also these kind of mechanisms to analyze the Alp-mediated process. We are interested in diboson analysis when one boson decay to leptons and the other part is an hadronic decay and decaying into to quarks. The process of these kind of processes is they have large branching fractions and they are sensitive in a small region mass from 400 GeV to 2000 GeVs. But the counts, they have large backgrounds from QCD and C plus jets, for example, which can be estimated by theoretical computations, next to linear QCD calculations, and or sideband data. So up to here, essentially the work of the analysis is try to understand as well as we can the standard model expectations, the standard model background, and try to look any deviations for these standard model predictions. In the case of resonant, it's like a bump over the background. And in the non-resonant case, is like a uniform distribution in the case of the invariant mass distribution of the PT or the PT. So to look at new physics, we start by taking and reconstructed data. I don't go into details about this, just to talk roughly about the experiment and reconstruction of the data in CMS. Everything starts at the LHC, where a bunch of protons circulate in different beams in opposite directions. They meet at point of collision with where the CMS is located, and they collide. So, after the collision, new particles, the created new particles leave signals through the detector. And for example, here CMS, this carton of CMS is like an onion with several layers capable of detecting different kind of particles, muons, electrons, charged hadron, neutron hadrons, and photons. And the most inner part of the detector is the tracker. It detect charged particles, the calorimeters, and the gas chambers to detect muons. So we try to collect all activities that the LHC delivered to the detector. As you can see, along of the years, CMS collect in this distribution. In yellow, this is represented by CMS. We try to collect all the activity, and among of the years, we collect more than 8% activity by with different So for that, we're required to look at all bunch of things, select the most interesting ones, and collect all the technical information to store and sort it for offline analysis. This is the principal function of the trigger, which basically accept or reject events of interest. CMS have two levels of trigger. The level one recognize parameters like charge, time, PT thresholds, patterns, and etc. And the high level trigger, which are algorithms to filter the level one objects and build complete events. These triggers are organized in menus, which are the sum of all objects, definitions, and algorithms to take a decision and build a complete event. We can adjust these thresholds in the triggers to be sensitive to electroweak or to search new physics. Once we collect the events of interest, we reconstruct all the data with algorithms that we call the particle flow. This the idea of these algorithms are is combine information from all detectors and trading information from low to high resolution detectors to construct objects and to deal like physical particles for the analysis in an easy way. So once we have these objects like physical particles, we look at in the reconstruction of the leptonic part in the decay. So we observe that the C decay is decaying to leptons. This could be muons or electrons, and as you can see, for both we have very good efficiency from low PT to very high PT. in the case of muons and electrons, this part is easy, but the hadronic part is more difficult. It's more difficult because and it's a problem that has been resolved along of the years, but not completely yet. As you know, the quark don't live alone in nature. They hadronize up to create stable particles that we see in the detector, like clusters in the hadronic, or in the calorimeters. Sorry. And for example, here, this mess is a decay of the of an hadronic event. As you can see here, the clusters of the hadronic, the red ones are the electromagnetic calorimeter, and the blue ones are the hadronic calorimeter. These tracks in green are the charged particles. So to analyze this kind of decays, we start like define a space, a region, to group all these stable particles, and in a cone that such that we can assign energy or PT in this special region. So we can also adjust the size of the cone, and which implies that the energy and the PT changes. And so hadronic decays produce other issues. Work with jets and heavy resonances means to go to the boosted regime, where a single jet has a PT more greater than 2.5 times the mass of the boson that we can look. So for this analysis, we can identify two kind of decays. The so-called result, where we identify in the detector two small jets separated perfectly, and the boosted event, where we see in the detector only one energetic fat jet or merge jet. So the challenge of this kind of processes is identify if this fat jet or merge jet it's coming from a real decay of the boson, or is produced by a QCD background. The standard techniques that we use in CMS to identify boson decay versus QCD are the pile-up mitigations, where we identify particles produced by pile-up activity. The jet grooming, when we recluster the jet, removing the soft radiation, look into the jet and define subjectiveness, which is a measure of how consistent is a jet with a hypothesized number of subjects inside of the fat jet, and the big quark type. For the grooming, the technique is the soft drop, which consists in identify two subjects, and then if the two subjects satisfy this condition, which depend on the PT, the separation between them and these parameters. So see, if they satisfy this condition, the fat jet is declared as a soft drop jet. Else, drop the softer subjects and iterate on a harder one. So we repeat the process, and in an iteration until we have the hard subjects into the fat jet. So these parameters C and beta are that the algorithms recognize what soft radiation, what the algorithms recognize as soft radiation and collinear radiation of the jet. And once we have finished to iterate in these processes, we have two subjects. The two subjects returned by the algorithm are used to calculate the soft drop jet mass, which is a very important parameter because we use this observable to define the signal regions of the boson once advance outside of the window mass of the boson. So here I show you three physical bosons. This is a simulation, but what we see how the physical bosons are separated from all the background QCD represented in the graph. So this signal region depends on the which boson are working. For example, the signal region 1 is traded with bosons like dot electroweak boson, and the signal region 2 for the subjectiveness. So the idea for this is we know how many final state objects to expect from boson decays. So we can look inside of the jet for the expected substructure. And for example, in the top decays, we expect 3 subjects, and in electroweak decays and Higgs, we expect 2 subjects. So for that, we define this new variable, which depends on the PT of the subjects inside of the jet, and depends also on the distance between them. This variable provides a measure of the number of subjects that can be found inside of the jet, with a low value of this variable is consistent with n subjects or fewer. And we can found that the ratio of this variable, the tau to 1, is a very powerful discriminant for boosted decays. In particular, in the analysis, we use a high purity cut, tau to 1 less than 0.4. And here you can see the ratio of the tau to 1, where the QCD background is represented in this black line, and is separated from the case of electroweak bosons. And this blue row is our plot for that. So the B tagging is used in subjects to separate heavy quarks versus light quarks, using the properties of the heavy quarks, like the large lifetime, the decay length, the displaced vertices, the large impact parameter between vertices, the non-isolated leptons, soft leptons or low PT leptons, and fragmentations of the jets. So among of the years, these techniques has been tuned in the round 1 and also in round 2. CMS use the PDTs, post decision trees, and now we use deep neural networks, different techniques of neural networks. So, in our analysis, in particular, we use this deep CSV, which is this technique. But these techniques are still in the state of the art, and they are discussed in several meetings yet. So we use this tagging to define a tag event, where a tag event is take a subject. If this subject satisfy medium requirements of these variables, and the second subject and the second subject satisfy those requirements of these variables. So we have a target event. So we work with events from run2 at DHC. We collect events from 2016 to 2018 at a center of mass energy of 13 TeV. Here, for example, I show you an example of boosted decay where we identify two muons on one side, and on the other side, the hadronic decay represented in single budget. So if we put together all these techniques, we start to select and categorize the events. In particular, we consider both posted and result events. The background is estimated by side and data, and the background estimated and the categorization of events is based on. So we start with electronic selection, two electrons coming from the decay of C boson. After that, we apply the boosted selection. If the event failed the boosted selection, we apply the result selection, and so on. If the event failed the selection, is removed. If not, we group the kind of boosted and result. And then we separate it in different regions, sidebands and signal regions. It depends on the decay. And we categorize these signal regions or sideband events in target or untarget. So here I show you the variables involved in the electronic selection. As you can see in this step of the selection, we have a very good agreement between the data and the Monte Carlo or the standard model prediction, which is represented in this green distribution. And the red line is the theoretical model of the ALP. In this case, is ALP going to CC. Here is the distribution of the leading PT, the subleading lepton, the invariant distribution of the dielectron, the dimuon, and the PT distribution of the dilepton, and the separation between two leptons. Some variables, some distributions of variables that are involved in the boosted selection, the ratio of tau to 1 for sidebands, signal region 1 and signal region 2. And here also we have a very good agreement between our prediction and the data. More variables involve the boosted selection, the dilepton PT, the invariant mass distribution of the dilepton, the separation of between leptons, the PT of the jet, and the separation between the subjects. And the same for the signal regions. 1, the signal region 2. For the result selection, the signal region 1 in the result selection, and signal region 2. So as you can see, we understand at a very good level our data with our standard model prediction and the categorization of the B-tagging events. Here, the plots are in sidebands, signal region 1, signal region 2, for the most be-like subject and the less be-like subject. And we group in different categories with no tag, plus requirements and medium requirements for the boosted selection and for the result selection. As I said, we estimate the subdominant background by fit the invariant mass distributions, considering 8 categories simultaneously: electrons, muons, boosted, resolved, tagged, and untagged categories. This is important to do in this way because improve the sensitivity of the analysis, and we can estimate how many events we expect in the signal regions. The other subdominant backgrounds are estimated from data. Here we are considering the lepton flavor symmetric backgrounds, which is determined from data, is considering TT bar, TW, WW, C to tau tau, and fakes. And this technique is tested against top quark-enriched control sample in Monte Carlo, and we found that we have a good agreement at the level of 96%. The other standard model backgrounds is determined by simulation. So now we are ready for the data. But before we talk about some characteristics of the since it's a counting experiment, we use Poisson distribution for pairs for only one beam, and then we construct a likelihood fit to fit all beams in the distribution. Here, this letter D represent the data measured or observed in nature, and is considering a signal and background, and the F function represent the model prediction from standard model. This F function depends on the two kind of parameters, which are the parameter of interest and the nuisance parameters. We when we fit the data, we try to minimize this likelihood function to find the parameter of interest, which is a measure of how is separated the new physics from the standard model background. And the other, the nuisance parameters are basically systematic and statistical uncertainties. For the uncertainties, we split into types: the normalization and shape. For the normalization, uncertainties affect uniformly the yields in all beams. For example, the luminosity, which if we vary the systematic uncertainty, the distributions are displaced up or down at the same time. And for the shape, uncertainty has non-uniform effect on beam yield. For example, the PT resolution, which affect in different way the invariant mass spectrum. So it's a beam shape analysis considering these categories. And to summarize, so we perform a maximum likelihood fit to fit the invariant mass distributions, considering 8 categories: electrons, muons, boosted, resolved, tagged, and untagged categories in a signal region and sideband simultaneously. The background only hypothesis is tested against the combined signal and background hypothesis. The systematics are included as nuisance parameters in the fit. They are plotted in the fit and independently for the different categories. The overflow bin in the invariant mass distributions, I mean the last bin, considers events up to 3,000 GeVs. For the ALPFITs, for a given value of the FA scale, events with mass greater than the FA scale are excluded from the fit. So now the results. Here are the invariant mass distributions of the data in the signal region 1 for the different categories, posted and tagged, result and tagged categories, for where the uncertainties are plugged in the feed. And here the signal in red line is normalized to 95% of confidence level. Here and the the linear ALP cross-section limit for an FA value of 3 dB. And the same one for the signal region 2, when the MALP, where the ALP goes to C and Higgs boson for the different categories again. And our distributions of the mass of the jet, in both the jets on top and on bottom for the dijet invariant mass. So here, as you can see, our fit is working well. We have a good agreement of the data. Our predictions are in good agreement. And finally, for that, we observe no significant excess of the graviton going to CC in this invariant mass distribution, and in the case of the W prime, when the W prime going to W as the but these limits improve the policy results in 2016 in this invariant mass region by a factor of 2.5 to 3 times in the mass results. As I said, non-significant excess is observed. For the ball graviton, the observation is not greater than 2 sigmas, and the W prime is not greater than 2 sigmas too, for the different values of the particles. And the results of the ALP can be shown in the couplings in the EFT model and as a function of the FA scale. And the expected and observed 95% confidence level upper limit of the cross-section going to of the cross-section of the process of gluon to diboson in phantom arms for an FA scale of 3 TB. We achieved restrict the theoretical values by 2 orders of magnitude. This is the first time that we this kind of processes is measured at the LHC. And right now, the colleagues from Madrid are working on to constrain the cross sections, but in vector Gaussian fusion. And that's it.
Thank you very much, Rogelio. We have time for questions.
Lo que sea, la alineación de mañana, México contra Argentina. No, lo que sea es un trabajo, yo soy experimental, es un trabajo, bueno, si no encuentran nueva física, al menos saben que las técnicas que usamos, pues dependen de muchas cosas, dependen de la reconstrucción de leptones, de la reconstrucción de jets, y la reconstrucción de jets es un problema. Justo, entonces podemos mejorar los resultados continuamente, mejorando la resolución de la reconstrucción de jets.
In that sense, what is your tag and your signal to study this, focus on this, right, so that you target like your functionality, and you target using process study this, research, for example.
No entendí.
Okay, sorry. What is your tag and your signal to study this process? For example, you say that you boosted target, but I cannot see, I can see the signal in your,
The signal.
yeah. in
The
the
signal
distribution.
is represented here in the red line. For example, in the boosted target, the signal here is not easy to see it, but it's here.
But you just reconstruct only your process, your one process in, for example, Higgs decays on to C, and the final states are leptons, no?
Yes.
Yeah. And you only use that process, or you mix with another process in order to improve your statistics, or not?
No, I only the process when the diboson mechanism decay to two leptons and two quarks.
Inclusive, all inclusive?
In different analysis. For example, in the linear case, we use to CC to L to Q. In mechanical analysis, we use C and Higgs to L to Q. The final state are the same.
Including when the lepton is a muon or the electron channel?
Yes.
Okay, thank you.
Thank you. I have a quick question. I know that there are some ideas to look for action like particles and UPC collision.
And UPC collisions were I don't know, because this kind of physics is very energetic. The PT of the electrons and muons are more than they have a PT greater than 40 kV. I don't need to UPC collision, and the electrons can achieve the PT state.
Thank you. Okay, we thank again the speaker. Okay, we move to the last talk of the workshop. Will be given by Marquis Sanchez, phenomenological analysis of we going to find left indicator. Please.
Hi, everybody. My name is Marcil Sanchez Garcia. I'm going to talk about phenomenological analysis of DC plus 2, pion plus muon minus, muon plus decay. And this work is in collaboration with Genaro Toledo, Ipunam, and Ivan Heredia from Simvestab. This work is based in this interesting paper. And I'm going to start. Online. First of all, we study the role of the parameter involved in the resonant region, it's decay, and we focus in the relative phase between rho and phi, delta rho phi, and we want from LHC theta and fit this parameter, and then we look observable insensitive to this phase, focus in forward bareback observable, and we analyze some general scenarios with this observable. Motivation. precise measure in this short sector, we allow to test new physics scenarios in an intermediate energy. This decay has been used as a reference channel in the understanding of suppressed modes. Knowing the full aspect of non-flavor changing neutral current process will help to identify the truly flavor changing neutral currents contribution feature. New fishy prospects in the Sharon sector are expected to be tested in the so-called off-resonant region, below of eta and above P. Okay, the long distance contribution of this decay is in two possible diagrammas. The first one is with based on vector meson intermediate state, is this first one. And the second option is when this process is mediated by a scalar meson. The amplitude of long distance is the top, and the A rho phi, A omega phi are constant that are in this way with the constant complete. This constant complete has been calculated in the individual process. For the other hand, the diagram of the with intermediate eta meson is with a loop, but we only consider a contact point in G eta mumu, and this has all information. The coupling for this is in this. Thank you so much. The corresponding coupling has this magnitude. Like I say, we first feed with the LHB data because the phase is a free parameter. So we did a shift fit and found the delta rho phi has a value approximately 0.44 with an error 0.21 given by fitting uncertainty, and 10% we have to consider for the data extraction. In this plot, we have the mu invariant mass, and the orange region is considering all the phase rho phi, and the line blue line is the central value 0.44 p, and the dashed line are the region between considering the error, and in the table has 3 regions where we calculate the long distance. The first one is considered all the phase, all values in the phase. The second one is considered the central value and the region in the error. The third one is considered short distance, and the last one is considered the interference between long distance and short distance. So the object was found observable that as insensitive to the phase. So we first consider angular observables. These cinematics has to be in this way. And we again have in this plot the Timon invariant mass distribution, but in the cinematic with the angular in the cos theta equals 0.1. This case is only for example, the more favorite region. And this is the long distance contribution. Equal, same that the last plot. Orange region is considered all the phase. Blue line is considering the fit, and dash line is considering the region with errors in the fit. we focus in the forward backward distribution, this observable, and in this case, considering the long distance, we have this form, the forward backward observable. If we take this in the cos theta equals 0.1. In the graphic, we have in the blue line the long distance, and the dashed line we have only considering phase speed estimation. Like we can see, in this case, was taken for all phase delta rho phi path. Like we can see, don't show is only one line, and the region between the only space phase and the blue line is 0.55. We consider other scenario with this observable. The first scenario, like we considered, was this process. This is to 3 pion. This because this is the first of all the mainly background in the decade like we are studying. For consider this decade was studied by focus, collaboration, and they analyzed with 5 resonance. Equal, same as other plot, we have the distribution in the d pion invariant mass, taking cos theta equals 0.1. And in this case, also we take the case with cos theta equal minus 0.1. For the other hand, we have the asymmetry, forward bar 1, taking in the cos theta 0.1. In this case, we have both taking only space and taking normal. And in this case, don't show difference. We have also take other scenarios, short distance in the standard model, and we take other scenario considering Sharge and Higgs in short distance. The first one in the standard model has this amplitude, and for the case the no standard model, in the Higgs sector and the Higgs, Sharge Higgs, we have this amplitude. For both case, we take the same. We calculate the forward backward observable, the distribution, and in the first one, consider the standard model contribution, that is this. And the second one is considered the Sharge Higgs like intermediate state in short distance. And like we can see, they show some difference, and the red dashed line is taking only space. We explored all of them, source, analyze the earliest data provides a first approach to the relative phase, delta rho phi, that it was 0.5 plus minus 0.24. Observable sensitivity to the delta rho phi phase will be also useful to keep the hadronic contribution under control. Forward backward distribution exceed no dependence in delta rho phi phase. Short distance contribution in the standard model, and in this model exceed distinguish future and model cells, which might be useful to understanding of the different contribution. Finally, Bell 2 may be capable of provide precise measurement of deep cross-pod observable with reduced systematic uncertainty given to the lack background environment in the EMOS E plus E minus collision, almost unbiased selection, and excellent particle identification. Thank you very much.
Thank you, Marcel. We have time for questions.
Hi, Marcel.
Hi, Jordan. How are you?
With respect to when you are considering the background, you show some intermediate particles that, right? Why didn't you consider another intermediate particle for the pion, for example, the raw meson?
The Robinson. Um, well, I understand in this case, in the focus collaboration, that we base this part on this article. They consider, they analyze these five resonance, and we put in this way, because the objective was show how distribute in the forward backward observable. But I don't understand very well your question about the raw. Can you be more precise or more descriptive?
Okay, why are you only considering that these five particles and no more than?
Well, like I say, because this is my answer again is because we use this article and they show only this, but I think there are more resonant and that will be interesting to consider more. Thank you.
Thank you. Is there any other question or comment? Thanks, Marcel, for the presentation.
Thank you, Gerardo, Tome.
Yeah, I have a question regarding your analysis when you consider the contributions of the Higgs chart article. Here, as far as I understand, you base your analysis in the two Higgs double model, right?
Yes,
And this, for other models, the result, this is a very nice question. I suppose that there should be very similar. You expect that can change a little bit? Or?
with different models about
yeah.
Higgs, considering Higgs or
Yeah, considering chart Higgs.
Sharkies. I don't know, but I suppose yes. Well, this was like example. It's not really serious. We have to study more about this. It's only an example in this moment, but if we will describe more precise result, we need to study more about this. But I suppose, yes, it will change in different model.
Thank you.
Thank you, Tome.
Thanks a lot. One last question. Otherwise, we can Marcel again.
Thank you very much.
Okay, at the end we did it. We have 2 minutes left. We appreciate that you are here in the last day. Very tired, maybe you travel today or maybe tomorrow. So, Karen is around to you can work to solve the workshop, but I think that here is Karen. Thank you for giving the word to Karen. Thank you very much for coming to Puebla. Amazing. Thank you.
So thank you very much to Mario for all this work and also to the organizing committee. And thank you all. I hope you have enjoyed and you have met a lot of new people which you are going to take for your future work and so on. For this, I am looking to, I'm very tired. I don't know. Yeah, not that excited, but okay. I think you really learned a lot. And we are having this evening two public talks. I hope you can also detail a bit more. We are going to organize also a proceedings book. So if you are interested in the next week, we are going to announce that. And also we are going to create the outreach committee of the education and also the gender committee. So for talking more about all these other necessities and activities that we have to perform as well as education. Thank you very much to all the presenters, all the professors that travel a lot from the other side of the world. And now that we know each other, we can stay. So thank you very much. Thank you for thanks to the organizers and have a nice life to stay. I will have a few minutes before. We have 5 minutes before Guillermo starts.